The idea of the lectures is the following. There is always something during tutorial where we where we try to complement a bit what we did. So it is on Thursday afternoon we'll do cosmological perturbation with Mathematica, and maybe Sushant will help with Maple, how to do these calculations. This is pretty important because we cannot just do background physics, that to study just if the universe is expanding or not, because this is at very, very large scales. When we start going to smaller scales, we start getting things which are not homogeneous and isotropic. As I said yesterday, the idea is the following, that at very, very large scales, more or less the universe looks homogeneous and isotropic. When we start going a bit at smaller scales, we make a zoom here, we will see that actually there are structures. There are different structures like this. So there are galaxies in some places, in some other places there are voids, etc. So this can be described because actually this is a small fluctuations in the sense that it is pretty homogeneous and isotropic, but there is small fluctuation in the density of matter. So it's like if you have some density T and you just consider some fluctuation which depends on the position, etc. So here you have a bit of overdensity, here you have a bit less than the density at very large scales. So you have some fluctuations of that. And because we know that the theory of general relativity links the curvature to matter, if you have a perturbation in the matter, this will produce a perturbation in the metric. So this is what we are going to study actually, the perturbation at the same time of the metric and at the same time of matter, and this will give us some equation. Now of course when you do perturbation theory you can go at the order you want. What we are going to do is linear order because it's much simpler. There are almost no one who is going at higher than that. Second order, the equations become extremely complicated, too long, but this is an interesting thing for someone who wants to dedicate a bit more time into that, because more you go in some at higher orders, more you go to smaller scales in some sense, more you have more precision. So if you have some variations which are too large, if delta rho is the variations of matter are too large, then you cannot describe it by this. For example, the density at the scale of the universe, it's like 10 to minus 29 gram per centimeter cube per volume. So it's a very low density. If you come to Earth, so you got very small scales here on Earth, the density is like 1 gram per centimeter cube. So we have a density which is much, 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 much larger than the density at large scales. So of course, if you want to study things at the scale of the Earth, you will never do it by this. Then you have to go to full nonlinear theory. So this is what is called the linear theory of perturbations. In the sense that we are going to write our equations at the linear order. So we will get some perturbation delta rho here, you will get some delta P of the pressure, etc. And you try to find an equation between them. And then you study how these perturbations are growing or not. So this is the linear order perturbation, and why it is important, because first it connects directly to observables, what you can observe, because you go at smaller scales. Secondly, it will give us also some conditions of stability of the theory. So that is very important to know if the theory is well defined or not. So this is the main motivations of the theory of perturbations. So as I said, when we perturb the T mu, you get a perturbation of the metric. So we are going to write it in this way, that our metric is some metric, which is the background, plus some perturbation. And what is this background? It's just our Friedman universe. So it's just this universe, and 0 here, the metric that we have seen yesterday. So we take this metric and we do some perturbation around it. So every time that I will put a bar means that this is the background, and then the delta of this is the perturbation. So this is going to be what we will extend. And of course, delta G mu. So this depends only depends on time, and delta G mu, of course, depends on everything, time and space, t, x, y, and z. Okay, so then we have to do these calculations. Now what we are going to do is to use some formalism which has been developed by Lifshitz, the same than in the book, Landau and Lifshitz, in 1946. The idea is that you can always make a decomposition, and we will see why this decomposition is very important. What you have, this is a matrix, and this is also a matrix, but with all components. So what we can do is that this matrix, delta G mu, which is a matrix 4 by 4, what you can do is that you can separate it into different components, which is the term here, delta G00, here it's delta G0I, delta Gi0, and delta Gij. What's happening is that this is like a scalar, this is like a vector, and this is like a tensor, a 3 tensor. And we will see why it is important to do this decomposition. It's called the SVT decomposition. So SVT is scalar vector tensor decomposition. So that was introduced by Lifshitz in the year 1946. Okay. So 1946, yes. So the idea is the following, is that delta G00 is a scalar. So what I'm going to do is that I will write it in this way. Minus 2 is just a convention. Minus 2 phi, because it's a scalar, so I will just write it in this way. It's just redefinition of the parameter. Minus 2 is a convention, because it simplifies the calculations at the end. Okay, delta G0I is a vector. And because of that, I will write it. I will put a scale factor in front. Again, it's a convention, Vi. And V is a vector. And delta Gij is a tensor. So because of that, I will write it as an A squared. Yes, I put an A squared of T times a function, a tensor Sij. So far we just do redefinitions actually. It's just writing the same things but in a different way. So our matrix, we can always write it as this term here, which is like a scalar. This column here and this one are vectors, and this one is a 3 tensor. So we can write it as a scalar, a vector, and a tensor, a 3 tensor. So far, this is the decomposition by Lifshitz. Now what we do is the following, is that we consider you might have certainly studied that, which is called the Helmholtz theorem. Helmholtz theorem, which says that if you have a vector, you can always decompose a vector actually. For any vector, so that has nothing to do with the theory of perturbations. For any vector, you can always do this decomposition. You can, for any vector W, you can decompose it into a longitudinal and a transverse component. So what does it mean? That you can always write it as two terms. One, I will write it like this, and one is like this, whereby construction the divergence of this is 0, and the orthogonal part is 0, the rotational of the parallel part. So when you have a vector, you can always decompose the vector into two parts. One part has that the rotational of it is 0, and the other one has that the divergence of it is 0. So this is called the Helmholtz decomposition. So, and because the rotational of the parallel one is 0, we know that omega I parallel can be written as the divergence of some scalar. We know that when we have the rotational of something equal to 0, we know that the rotational of the divergence is 0, so this can be written as a divergence of an object, of a scalar, actually. So what we say where B is a new scalar. So what we say is that our object here, you can always decompose it into one orthogonal part, which has a divergence which is equal to 0, and the other one you can write it as the divergence of some scalar. That is a very general decomposition for any vector. And this has nothing to do, again, with the theory of perturbations, so you will always have this property. For any vector, you can always decompose it in this way. So you have two parts of the vector. Okay. So going back to our object here, we have a scale factor times a vector. So this vector, I can decompose it into this orthogonal part, which we call usually a pure vector, plus some scalar. So this term here, I can write it as a of t times some vector that I called si plus some divergence of a scalar that I called b. With the condition that the divergence of S is 0, which is the condition we had here. So far, fine? Yes?
So how can we write delta G I0?
This one?
Delta G I0.
I0. This one is exactly the same. This matrix is symmetric. Other questions?
Then this symbol in the last above.
This here?
Yeah.
This is the gradient actually is this. Okay, So this is the decomposition, the Helmholtz decomposition of one vector. How does it work with this tensor? We have two indices. So each index we can consider it as a vector. So each index we decompose it into parallel and orthogonal part. So this is exactly the same logic. Let me take this with me. So exactly the same for the Sij. I don't know if everyone can see, because when I'm here I don't see at all because of the light. So people who are here, or maybe I should use, there is light or no?
I think it's fine.
Okay. Yeah. Okay. So the Sij, I do exactly the same decomposition, this Helmholtz decomposition here. Like for a vector, I decompose it into a parallel one and an orthogonal part. The parallel one has this property, and the orthogonal part has this property. So I will do the same thing, but for each index here, I have two indices. So the I can be parallel, the j can be parallel. So I will write it like this, parallel, parallel. So then I have also one is parallel and the other one is orthogonal. One is orthogonal, the other one is parallel. And one is orthogonal, the other one is orthogonal. So you have four terms now in this decomposition. Exactly the same logic, but each index you decompose it. So you put it in this way. So as before, the parallel part comes from a scalar. Where is the parallel part? Is this one. The parallel part comes from a scalar. It's just the gradient of a scalar. So here it will be the same. The parallel part will come from a scalar. Okay, so how you put it as a scalar? You have two scalars that you can write. Again, the factor 2 is just matter of simplicity for after. So this time you don't have the gradient of a scalar, but the double gradient, because you have two indices. But you have another possibility, which is the trace part, like this. Again, the factor 2 or minus 2 is just matter of definition. So the factor 2 minus and things like that are just definitions, actually, just for simplicity. Yes?
Del dot omega perpendicular 0, is it reducing some or it's not reducing? Because B has 1 and component wise you could consider W has 3 components. So B has only 1, so SI should contain 2 others. So
Exactly.
Del, this, is it reducing some?
Yes. Yes, exactly. I wanted to count degrees of freedom at the end, but let me just then say it now. So what he's saying is that we have a vector. We have a 3 vector. So in a vector, we have 3 components in the vector. So we have, in some sense, 3 degrees of freedom. And we decompose it into different things, so we should have 3 also. So what we have now, we decomposed it into 2 terms. B is a scalar, so this is one of the degrees of freedom. So the SI should have the 2 other degrees of freedom. Then we have 2 plus 1 is 3, and the vector has 3 terms. Now the SI is a vector, so a vector should have 3 terms, but at the same time, we have this constraint. So this constraint says that all components in the vector are not independent. So we have a 3 vector like A, B, C, but actually because of this constraint, so the gradient, the derivative of this plus this plus this is equal to 0. So these 3 are not independent, so actually there are only 2 which are independent. So this term here has 2 degrees of freedom, And this one has 1 degree of freedom because this is just one number, this is just a scalar. So at the end we have 3 like a vector should be. So at the end I'm going to count all degrees of freedom because it's a 4 by 4 matrix, symmetric, so we should have 10 degrees of freedom, which are 4 here in this diagonal. Then there are 3, 2, and 1. So this is 10. The other ones are symmetric. So we will see that we have the 10 degrees of freedom that we needed at the end.
That means in this Helmholtz theorem, what you are doing is that you are connecting your some scalar field with your vector component.
Mm-hmm. Yes, it's just it's this actually. It's really to say that these 3 components here, one I can really decompose it as really a scalar. One is a scalar and the other one will be some kind of a vector. I don't talk much about what I mean by scalar and vector because this has to do with the invariance and some transformation. That if I do some transformation, scalar should not change. Yeah. And the vector will get some factor, etc. Tensor get a double thing, etc. But this is what it means, really. So this theorem says that I can always decompose things into one which is a scalar, which means really it's invariant under these transformations, which are going to be rotations. And this will be a real vector, that really it gets the right factor when we make a rotation. It transforms as a vector.
Okay, yeah, that means you are decomposing in like in vector you have 2 quantities, one is magnitude and one is direction. So you keep magnitude as a scalar at one side and then direction would be in S.
Yes, yes.
Your
Yes,
vector part.
yes, it's something like that. It's not exactly the magnitude because it comes as the gradient,
yeah, that's right.
but it's the idea, exactly.
Something like that.
Exactly, yes.
Yeah. Similar to that.
Mm-hmm. So the first term, which is the parallel one, we can write it like this with 2 scalars because you remember that parallel component is always a scalar as we saw before. Then we continue the ij, I'll do the parallel orthogonal. So what we know is that this I can always write it. When you have parallel, it means that you have the gradient of something, and the orthogonal means that you have a pure vector. So you will have a gradient of a pure vector. So you can write it in this way with the condition that this is a pure vector means that its divergence is 0. I should not write covariant derivative, sorry. So this is what it means, and you will get exactly the same thing for S ij orthogonal parallel. So it will be the same thing with just dj fi with the same condition. So we are building it by hand, but you understand that parallel means gradient of something. Double parallel, it's a double parallel. It's a double gradient of something. So here one is parallel, so it's a gradient of orthogonal, it's a vector. So this is what we should have. So we have 3 components and is left only the last term, the orthogonal. Which is just a pure tensor with the conditions that its divergence is 0 and also it is traceless. And why we take it traceless? Because actually we took the trace here. So with that we decomposed completely the metric. So let us summarize what we have. In our metric now we have the following. This is a minus 2 phi. is what we just wrote in a different way. This term here is an A of t, some vector that I called Si plus dy of b. And the same thing here. The delta Gij is everything there. It's a squared Sij, and Sij is all what you have there, the summation of the four terms. So now let's count the degrees of freedom to see the total. So how many scalars that we have in our theory, in our metric actually? So how many scalars that we have? We have one scalar which is phi. So we have phi, which is a scalar. We have b, which is also a scalar. And there we have e and we have psi. We have these two scalars here, e and psi. Okay, so we have four scalars actually. How many pure vectors means that each vector doesn't have three components but only two, because there is always the condition that the divergence is 0. So how many vectors do I have in my, I have this vector Si, I have the vector F, which is there. Okay, so we have two vectors. And how many pure tensor is just the one pure tensor, which is the Hij. Okay, so with this we have everything. The scalars, each one comes with 1 degree of freedom. So we have 4 degrees of freedom. 4 degrees of freedom. The vectors, as we said, each one comes with 2 degrees of freedom. So we have 2 plus 2 is 4 degrees of freedom. Now the tensor, we have to calculate what it is. It's a matrix, 3 by 3. So a matrix 3 by 3 symmetric, you should have 6 degrees of freedom, but it has first this condition here equal to 0. So you can take it for j equal to 1, 2, 3. You have 3 equations. So you have 3 constraints. And you have also the trace equal to 0, which is 1 constraint. So we have 4 constraints. So you should have 6 degrees of freedom, but actually minus 4, the constraints there, so you have 2 degrees of freedom. So actually there are only 2 terms which are independent. For example, this one and this one. The others are not, because you have these conditions on this matrix. So at the end, you have 4 degrees of freedom, plus 4 plus 2 is 10. And this is what we should expect from a matrix which is 4 by 4 symmetric. You have these are the component of this matrix. 4 plus 3 plus 2 plus 1 is 10. It's symmetric, so this depends on this. So these are the 10 degrees of freedom. So we didn't lose anything. What we did is just a decomposition. And with that, it will be much simpler. So we take our matrix, which is 4 by 4. It has 10 components. And these 10 components, we are going to make a separation, a division of these terms into 4 scalars, 2 vectors, and 1 tensor. That's the idea. And why we do that is because when you do the theory of perturbations, each of these degrees of freedom are going to give an independent equation. You will get an equation for the scalars, completely separate from the equation for the vectors, and another equation for the tensors. They don't mix at the linear order. At the nonlinear order, they start mixing. And that's the interesting thing, that then we can study them separately. I don't have to study all the perturbations at the same time. I will study each perturbation separately. So for example, I can focus only on scalar perturbations. And I study that. then I can study only vector perturbations, then I have an equation, and then only tensor perturbations. If you want, you can write everything, and you will see that the Einstein equations, they give separate equations, and that is perfect. And this is why we do this decomposition, because really it separates and it simplifies life. So physically, what it means, these are going to be related to the gravitational potential. These are the scalars. So it will be mostly important for the formation of structures, that we have some gravitational potential and matter is falling into this gravitational potential, and we get clustering and we form structures, galaxies, and things like that. These vector perturbations, and the source of them will be the density of matter. So we found an equation which relates this to the density of matter, the delta rho. So if we have some density of matter, this potential increases, etc. The vector here, we will find that there are no sources for this. So actually, there is nothing in the T mu nu, in the matter sector, which can produce, at least for standard matter, which can produce this kind of object. So if we start with the universe, which has some value of this will decay with time, and these perturbations will just disappear. We can show it. I don't know if I have it in my notes. I think I focused mostly on the scalar perturbations, but I will give a reference for that. So you get an equation and you see that this decays with time because there are no source to these perturbations, so they are in some way not relevant. The other one is this. These are tensor perturbations, and they are the gravitational waves. The gravitational waves in cosmology. We are not talking about black holes. So these are going to be, for example, the primordial gravitational waves produced during inflation or during expansion of the universe, etc. So these are the other perturbations, and we are still looking at them. We haven't observed them yet, these fundamental primordial perturbations that we hope to observe in the CMB. So these are physically what they mean. Each one has a particular meaning. This is mostly the gravitational potential. These are principally related to some kind of rotation and things like that, but they are not sourced, so they decay with time, and this is just the gravitational perturbations. Okay, questions so far? Yeah, okay, so yes?
With tensor, you are telling there is a gravitational perturbation. It means that it will also perturb geometry.
It is the geometry, actually.
That's right. That is okay. Yeah, that I know. But what do you mean by perturbation in
perturbation?
Tensor Hij means it's a perturbation in gravitation, or what you?
Yes, it's the metric. So, and the metric is the gravity.
Yeah, that's right.
So this is what it means, a perturbation in the metric, but here in the gravitational waves, what it means is, so we see that first of all we have 2 degrees of freedom. And we know that in gravitational waves we have 2 degrees of freedom, which is the cross and the plus degree of freedom. So what it means is that if you have some particles of matter that perturbation passes, then they will oscillate in some way because of these gravitational waves which is propagating. Okay? But this is a deformation of the space-time which propagates. So this will produce an effect that we can observe on the matter. So matter will kind of oscillate in some way because that wave is passing. So this is the degree of freedom.
But there is no much importance of vectors.
No. The main reason is because if we write the equation, so if we write the Einstein equation, so Einstein equation is, let me write it now with the Einstein tensor, G mu nu equal to T mu nu. So we do a perturbation of that, and we get the perturbation in linear order like this. And actually here, I consider some perfect fluid with matter or radiation, etc. So it has some density, it has some pressure. All these things are scalar quantities. So they produce only scalar actual perturbations. So I have a perturbation of density, perturbation of pressure, and things like that. But I don't have something which is a perturbation of the vector which can actually source these terms which appear here. So I will get some equation equal to 0 for the vector things, some stuff, etc. equal to 0. And that equation we can show that then these vectors, because they have no source, they just decay in time actually. So they are, in some sense, maybe they were very important in the early universe. We don't know what are the initial conditions. Maybe the universe started with these perturbations which were very large, maybe.
Yeah, that's right.
But we know that if they were very large, maybe they affected the early universe, but then after that they decay. So today, at least for structure formations or dark energy stars, they are not important. But maybe they were important in the early universe.
I have a confusion. Is the counting for the full metric goes like same as we do here? I am confusion on this regard because we know with this diffeomorphism and all these things beyond identity to consider. We left with only two.
Yes.
And here we find it's all are independent.
No.
Is there matter causing these extras? Or
Yes, exactly. Exactly. So yeah, they are not new degrees of freedom.
If we switch off the matter, all these things only.
No, but actually we don't have all these degrees of freedom. First of all, I will use now the diffeomorphism to kill some of them. So we will kill that, and then after that there are also the constraints which are coming from the Bianchi identities, which are killing the others. At the end, we need only 2 degrees of freedom. That's for sure.
Physically, we will.
Yes. The other ones will be just produced by matter. They are actually degrees of freedom coming from matter perturbations. But now I will actually, so as I said, I'm going to focus mostly on this because they decouple from the others. So it's relevant for formation of structures and things like that. So I will focus on that. But we will see for the others is that these 4 are not all relevant in the sense that they are not all physical. We can always kill some of them. So this is the gauge freedom actually. We always have some freedom and we can kill them actually. So not all of them are physical. So this is actually what I'm going to do now.
Excuse me, sir.
Yes.
So could you please summarize that, like how we have calculated a degree of freedom for tensor?
So for tensor, so we have a 3 tensor. So it's a matrix which is 3 by 3, which is symmetrical. So we have 3 to 6. Originally we have 6 quantities, but we have 2 constraints on them. One constraint is the following here. You have a summation on I, but j is independent. So you have a first equation when j is 1. You have a second equation when j is 2. And you have a third equation when j is 3. So actually these are 3 equations. So there are constraints on this thing. So we have 3 constraints, and the other one is the following. You say that it is traceless. So h11 plus h22 plus h33 is 0. So this is another constraint on the h. So you have 3 constraints plus 1 constraint, you have 4 constraints. So 6 minus 4 is 2. Yeah.
So scalar fields, we will take them as massless, massive,
We don't fix them. They can be massive, they can be massless, that the theory will tell us, but we don't fix them. We just have a field, which is just the perturbation of the space-time, and then we calculate, and at the end we get the equation which is there. If this equation gives a mass, it's a mass.
Physically, we don't have massless fields.
We don't have massless fields.
Massless scalars.
It's not a matter. It's not matter. So we should not interpret it as matter. It's geometry. So, for example, phi is just the gravitational potential. Like when you write Gm by r, this gravitational potential. So this is the scalar, for example, phi here. So it's not a matter field that you will say that it has a mass or not. It's really just geometry. So it's a bit different than.
It's a function of x, y, z.
Yes.
Yeah.
Yes. Of t, x, y, z. Huh?
Not quantum field, classical.
Yes. Okay, so what I'm going to do is that, as we said, this nice decomposition makes it easy because I can work these perturbations in an independent way. The simplest one are tensor perturbations. So they are easy to calculate actually. But let me go on the most complicated one, which is a scalar one. So this is why I'm doing it. The other ones, whatever you see now, if it looks complicated, in terms of calculations, because now we passed more or less the difficulty, the scalar one is really the most difficult one in terms of calculations. But you can do it with Mathematica, and this is what we will do. So the metric, let me write it with just the scalars. It will be like this. 1 plus 2 phi dt squared. So I'm just putting it a bit in order. Plus 2a of t dy b dt dx y plus a squared of t, and then you have 1 minus 2 psi delta ij and plus 2 del dij e dx y dx j. So this is just rewriting the metric that we found for scalar perturbations. So this is scalar perturbations. Okay, so far this is what we have with the 4 scalars, phi, b, psi, and e. Okay, so what is the freedom that we have? You remember that each observer, this is relativity, so each observer can have a different time. The time is not the same for an observer and for another. So let us suppose that we have a function f of t. Let us suppose that we have some function f of t. It can be, for example, the density, the pressure, anything. And let's suppose that there is another observer. So t is the time of observer 1. And let us see that capital T is the time for an observer 2. And what is the relation between them is that this is equal to what I wrote plus some. There is some transformation between both times. Each observer has a time different, and there is a transformation between the time of the observer 1 and the time of the observer 2. Okay, so what is this giving? What's happening is that you have the function f of t. Now f of t is equal to f of t minus delta t, and if delta t is small enough, you get something like that. And this, you can say that this is some f of t plus some perturbation of f. So what I'm trying to explain is the following, is that I had a function which depends only on time. The only dependence is time. I'm looking to another observer which has another time, and for the new observer, they appear like if there is some sort of perturbation, which comes just from the transformation. So what means, it means that I can generate perturbations just by changing observer. So that is of course not physical. It cannot be physical. That I have an observer which for him the universe is homogeneous and isotropic. I'm going to another observer, for example an accelerating observer, he will not see the same thing. He will not see that it's homogeneous and isotropic. He will not look at the universe in the same way. So for the second observer, it looks like there is some additional perturbation. So we can generate perturbations just by changing from an observer to another. But if we can do that, we can use this, it's called a gauge freedom, we can use that to kill some of these observers, some of these scalars, by going to a particular observer. So we have actually 4 scalars, but if we choose in a smart way some observer, we are going to kill actually 2 scalars. So that is the gauge freedom. That is the interesting thing, is that we have always the freedom because we know that physics does not depend on the observer. So I can always change and go to some observer where physics is simpler. I can work with that, but if I can simplify the problem, let's do it. So this is what we do, is that we go to an observer where we can kill some of these perturbations. Okay? So that is the idea of this gauge freedom. So what we are going to do is just to do a transformation of coordinates. So we have an observer, we do a transformation of coordinates, it can be a rotation, a translation, or something much more complicated. We change to another observer and we see how things are changing. And according to that, we will see that some of the terms can be killed. So we kill them and then we work with that particular observer which is looking to the universe in a particular way, but we know that at the end what he will observe is the same that what we should observe, because the physics should not depend on the observer. It's just that for this observer, the calculations will be simpler. I don't know, this is a kind of critical thing. It's quite important, that gauge freedom. Okay, so
as these fields are not physical, so we have to kill all of them, or we are preserving 2.
We are going to kill all what we can kill. So we will see that we cannot kill them all, actually. It's impossible. We will see that when we do these transformations, some of them can be killed, some of them cannot. This is only the mathematics which is going to tell us that.
Yes, sir, that particle field does not allow these lossless scalar fields.
The what? Particle physics?
It does not allow.
No, it's not a matter field. It's not a matter field. So particle physics describes matter fields. So all the fields which exist in nature as matter, but not geometry. Particle physics doesn't say anything about geometry. These are just geometry. As I said, the scalar field can be just the gravitational potential, for example. So it's not something which is described in any way by particle physics. It's just a mathematical thing. We just look at it as scalar, vector, and tensors. It gives the simplicity of calculations, and at the end, we get some observable. But then at the end, what we observe, we don't observe this. No one observes that. We observe the distribution of matter. We observe galaxies. We observe voids, etc. This is what we observe, but this, we don't observe them. So this is just a mathematical trick. We do the calculations, and at the end we see what is the observable. And the observable is the density of matter, the delta rho. That is what we will observe.
So that means the scalars must be related with density, no?
Yes. This is the equation that we will get, the equation which comes from general relativity.
Yeah.
So we do the perturbations, and this will come as derivatives, blah, 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 etc., equal to T mu, or the perturbation of T mu. And this will give us actually that. Okay.
So
Yes.
here what I feel that as you means mentioned that our physics is not observer dependent.
Mm-hmm.
Means then I think you are going to kill all this artificial effect.
Exactly.
And you will find some genuine
Exactly.
observer that which will be universally true.
Yes. Yes.
Like standard candles, no? Supernova.
Yes. Yeah. No, there are 2 things. One is we can work with some sort of artificial observer where we redefine these quantities in such a way that each of these quantities is independent of the observer, that each observer will have exactly the same quantities. So this is the theory of perturbations in gauge invariant formalism, it's called. So that you get an object which does not depend at all on the observer. The other way, which I will do now, and this you get 2 of these scalars, which are called the Bardeen potentials. So for the ones who want to look at it a bit more, it's called the Bardeen potentials. and you get only 2. The other one is, because it's a bit simpler, is to say I'm just going to kill 2 of them because I'm going to a particular observer. So this observer and this observer, they don't in some sense have the same thing. One has 4 scalars, the other one has only 2, but we know that physics doesn't depend on that. So I will do it like that. So people did it in different ways, and at the end we get the same results, of course, because it's independent of that.
So
Yes?
in the ring left, the background is different.
In the what?
In the ring left, it's the accelerating frame.
Yes.
So background can be different. So how is it different from this perturbation? Means we cannot have a observer dependent background.
We cannot have an observer dependent background. Yes.
So but
Yes.
in the accelerating frame, if we are
Yes.
then there is a thermal radiation.
Yes.
So that is different from the static observer.
Yes.
So how it is different from this case?
You're saying why, if I understand your question, you're saying why the accelerated observer observes
थोड़ा zero बोलो ना, मैंने भी सुना।
हाँ जोर से बोल।
So actually in the accelerating frame, so
Yes.
there will be observe some non-zero thermal radiation.
Yes.
But that is zero for static observer.
Yes.
So in that case, it is background is observer dependent.
This is not in the framework of GR. GR is general coordinate invariance, na?
But that is different in the Unruh case.
What you are telling?
Unruh radiation.
Huh?
Unruh radiation.
Now what he's saying is the following, is that if, let us suppose we have an observer like us here, we are static, and we observe something, etc. Now if I start getting an acceleration in that direction, what is happening is that I will receive some radiation, which is called the Unruh radiation, just because I'm accelerating. It forms actually some sort of horizon, because we accelerate, so we cannot see the full universe. And because of that structure, we get some temperature which kind of equivalent to the Hawking temperature. Let me think about it, and I will say that later on. So the thing is, we have these 4 scalars, and we know. So far we don't know. We will show that by the mathematics that some of them actually can be killed. So what we do is that we change the coordinates in the sense that we have the coordinate system x mu, and we change it to another coordinate system x prime mu, which is any time of function of x. Before any transformation, we can do some transformation which is just a Lorentz transformation, a rotation, a translation, anything we want. So for example, if it was just a translation, this will be just x mu plus some constant. That will be a translation, for example. So we can imagine any type of transformation. Because we are doing linear perturbation theory, I'm going to do also a linear change of coordinates. I'm not going to do any transformation, but just a small transformation, like a small rotation by an angle delta theta, or small translation, or small boost, etc. But at the same time, because I'm interested only into scalar perturbations, I'm just going to look to the transformation of coordinates which are scalars, because the coordinates can be also shifted by a vector, like here. So I'm just going to look to scalar change of coordinates, which means that the scalars are the following, that I can change the time. I'm just looking to a linear thing by some scalar alpha, and I can change the coordinate xi by some coordinate xi plus delta ij dj of beta. Let's write it with an index here. So we can make this change of coordinates. These are small perturbations, small actually change of coordinates. Just the time is shifted by a constant, and the position is shifted by the gradient of a scalar also. So these are the only scalars that we have. All the transformations will be vectors. There are no tensor change here because we have only one index, but we can have either a vector or a scalar, and these are the transformations that we can look. So we can look to these transformations here. So the time here changes by plus alpha. Alpha is a function, it's a scalar. And beta also. So we make these transformations here and we see how things are changing actually. This is the only thing we have to do. And so now I skip a bit the calculations. You will find them in the notes. And this is how things are changing.
Sir,
yes?
we are doing transformation here. Are they specific or we can change with other transformations also?
Which other transformations?
We are doing transformation xi plus
Yes, of the coordinates.
these are specific or we can change?
No, they are not specific, but they are the only ones which are scalar changes.
The second one we wrote there.
Alpha and beta are scalars, no?
Yes.
Yeah.
So what is the logic behind this transformation?
It's
How we will get, we have to transform like that.
yeah. So when we have a change of coordinates, we can change time x, y, z. So now when you change time, you can, okay, that there is not much of choices. But when you change the position, you can change it by a vector, like a translation. I can add here xi I if I want. So I just shift it by a vector. Or I can change it by the gradient of a scalar. Okay? This transformation of coordinates by some vector will influence only vector perturbations because it's a vector. So it doesn't mix with the others. So I don't want to look to this type of change of coordinates. I'm looking only to scalar type of perturbations or scalar type of change of coordinates in this case, sorry. Only this will affect the scalar perturbations. That's the idea behind it. So we are working in a consistent way with only scalars. Then if we do vectors, we work in a consistent way only with vectors and also for tensors. So then you have these transformations and you see how things are changing. So for example, dt changes into dt plus alpha dot dt plus dy alpha dxy. This is how dt changes. Okay? Just take the differential of that. So you replace the dt here and you see how things are changing actually. So this is what you have to do, and it's a small problem to do until you will get the notes. You can try to do it before, and then you will have the details in the notes. So each of these scalars is going to be shifted because of this change of coordinates. Phi changes into phi minus alpha dot. B changes into b plus alpha over a minus a beta dot. E changes into e minus beta, and psi changes into psi plus h times alpha. So this is how actually the scalar quantities that we had, they get transformed actually, and a transformation of coordinates in the metric. So then we see things that, for example, this one is quite interesting. I can always change the coordinates in such a way that this is 0. If I change the coordinates by replacing beta by e, so I transform, I go to a coordinate of a coordinate system where I can always kill that. So that is always possible. I just have to choose beta equal to e. So now beta is fixed. I cannot play with it anymore. What I can play with is alpha. So beta is fixed, is here. So then I can either kill this one by choosing alpha, or I can kill this one. Is it with an alpha or an alpha dot? It's alpha. So I can also kill this one, or here. This one is a bit more tricky, because it's, you don't fix completely alpha. In the sense that, imagine that you choose an alpha, which kills that. I can always add, imagine that you choose alpha in such a way that alpha dot plus is equal to phi. Now if I choose alpha plus some constant, it will be also solution of this equal to 0. So alpha is not completely fixed. It's fixed up to some constant. So because of that, it means that I still have some freedom in my change of coordinates. I can always add a constant, and my freedom here is not fixed completely. So this is why choosing this equal to 0, you can kill phi, but you don't fix completely the freedom that you had. So we want to fix completely the freedom, to fix completely the gauge. So what you can do is kill beta, you kill E, and then kill psi or B. So depending on people, you can choose one or the other. So each one is called a different gauge, and what I'm going to use is what is called the Newtonian gauge, where you kill E and B. So again, E, you can kill it with beta. Once you replace here, you can kill this by choosing alpha. So this is the Newtonian gauge. You kill B, and you can kill E. So this is what you have.
What is A? A is a vector. Alpha upon A, B is equal to B plus alpha upon A minus A beta dot.
Sorry, where?
Here, this equation. A is a vector, or what is B plus alpha upon A?
Yeah.
What is A?
A is a scale factor, sorry.
Okay, scale factor. Okay.
Yes, sorry. Okay, so this is something that you can do once, and then you don't have to do that all the time. Then you just say in your calculations, I use the Newtonian gauge, which means that I choose a particular system of coordinates where I kill E and B, so my metric becomes just this, actually. Okay, so these are the two scalars that we have, phi and psi actually. So then they are much simpler theory. So then you can use some other gauges which are called synchronous gauge, etc., where you kill psi and you keep B, etc., so you can play as you wish. But this is a quite standard gauge, and then you work with that. I don't know if you have questions or two here. So this you do it in some way once in your life, and then you can say, okay, I work in Newtonian gauge and I work with then these perturbations for the scalars. So now we have something. Remember that phi and psi are perturbations. So if you want, I can put some epsilon to say that they are small quantities. This is how I do it with Mathematica. You put an epsilon and then you make series expansion with Mathematica. It goes at order 1, for example, and you do the perturbations. So when phi and psi are 0, you have just Friedmann universe. Otherwise, you have some perturbations. So now what you have to do is just calculate the Christoffel symbols. And you write them at the first order of perturbations. So you write something at the order 1 in phi and psi. You don't go at second order of perturbations. For example, the inverse of the metric. So the metric is the following. So here you have minus 1 plus 2 phi. So the inverse metric, because you need it for the Christoffel symbols, we will do that with Mathematica. Because it's a diagonal matrix, the inverse is just 1 over this. So it's minus 1 over 1 plus 2 phi. And then this you just expand it at the first order is 1 plus 2 phi. or minus 2 phi. Minus. So you just expand it at the first order and you don't go at second order of perturbations, okay? So once you do that, you can calculate the symbol, Christoffel symbols. They are also in the notes, and I did it as usual with the geodesic equation. Then from that, you can calculate the Ricci tensor, the curvature scala, everything at the first order. And this is what you get at the end. So at the end of these calculations, what you get is that, for example, G00, you get minus 3h squared, which is just the background quantity, and plus C6h squared phi plus 6h psi dot minus 2 Laplacian of psi divided by a squared. And this is at the first order. And then you calculate G0I. Again, at the first order, you get 2 over a squared dy h phi plus psi dot, and G0I is minus 2 dy h phi plus psi dot. And the last one, Gij, is delta ij, 3h squared plus 2h dot minus 1 plus 2 phi plus 2h phi dot plus 6h psi dot plus 2 psi double dot plus delta ij Laplacian of phi minus psi divided by a squared minus 1 over a squared dy dj phi minus psi. Okay. So this is the calculations at the first order, and remember that we have the equation which is g mu equal to 8 pi g divided by C4 T mu. So we have this part here expanded at the first order. We just need that the energy momentum tensor expanded at the first order also, and then we just equal both of them and we'll get our equations for phi, psi, etc., the differential equations. So what we need now is just to make a perturbations of the matter sector. So this is the next step, if you have questions so far. Okay, so we have 20 minutes. I will then go fast on the part which is about matter perturbations. The logic is the same. So the logic is the same, is that you have a perfect fluid. We started with that to get the Friedman equations. So when you have a perfect fluid, as I said, the background quantities, I will always write them with a bar. So the background is the density Okay, so this is the background quantity, and actually the u mu. Bar means always, and this is the velocity field. And density, pressure, everything with a bar means that there is, it's a background quantity, it means that they depend just on time. Pressure also on all these quantities. So what we want is just to write that T mu is some T mu bar plus some delta T mu. So we want to find what is this perturbation here of the matter sector in the same way that we did for the gravity sector about the metric perturbations. So this is exactly the same idea. We say that again the velocity also will have a perturbation. So you have a perturbation of the velocity, you have a perturbation of the density and of the pressure. So the density will be the background, the pressure will be also a perturbation like that. And all perturbations depend on all space-time, and all background quantities depend only on time. So you do these calculations. I will skip the details. They are in the notes in order just to go a bit faster. And what you get is the following. Let me, the delta u mu, you can show that it will be 1 minus phi vi divided by a, where v is the perturbation velocity. So maybe I will just explain it without going into the details. You will find them in the notes. That this is the background quantity. We don't have velocity. There is just something in the time component that time is passing. Okay, and now we have a perturbation, and the perturbation produces an effect here, which is a velocity. The object has a velocity v, and you have also this term here, which comes just from the normalization of the 4 vector, which you always should have. So just considering this, actually you get this perturbation there. And so v is the velocity, because originally of the matter, yeah. So originally you have an observer where it's called the comoving observer, which means that it goes with the expansion of the universe. So now we produce the perturbations. So then you start seeing that there is actually some velocity which is produced now, because you are not anymore comoving. So that is this velocity, and the phi is just the same phi that we had before.
Okay, yeah.
And and the perturbations of density and pressure. So from that you get that delta T00 is just minus delta rho. Delta T0I is A density plus pressure Vy. Delta Ty0 is minus density Vi divided by A, and delta Tij is just the perturbation on the matter. So also you will have the details of that, so let me just skip it a bit fast now. So this is the perturbation of the matter sector. It follows exactly the same logic, and then you get that. Okay, so these are the perturbations, and remember that you need this equal to that. So the first thing that you see, let's look to the equation Ij, which means this equation. This equation Ij, there, the perturbation has only a delta Ij. So everything is diagonal. You don't have anything off diagonal. So, but here you have something which is diagonal. This one also, but not this one. This one is not diagonal. It doesn't have a Kronecker delta. So which means that this is equal to 0. If we have this equal to delta Tij. So what I'm doing now is that I'm solving this equation, and according to this, I have something here, delta Ij, which is all the first line here, plus this term here, minus a squared dy dj phi minus psi equal to delta p delta ij. So what we get is that this is equal to this, and this should be equal to 0. That is what we get from this equation, because it's not diagonal, and the other terms are diagonal. So the consequence is that if we go to Fourier space, what you will get is just some ki kj times this equal to 0. So that means that phi is equal to psi. This is what you get from the first equation, actually. That is an extremely important thing, because this is something that GIAN says, but in modified gravity you don't have it. So if you have any modified gravity theory, you can do the calculations, and at the end you will get some difference here. These two potentials that we had in the metric are different, and that has important consequences, because one potential is the phi here. It's important it's the gravitational potential. So it's very important for formation of structures. So when you study the structures in the universe, you see how the galaxies are forming, etc. You can get what is phi. The second one is related, actually most exactly the summation of both, is related to weak lensing. When you have a structure, so there is light which bends because of what? Of the summation of two potentials. So now if you observe both of them, at the same time you observe galaxies, and at the same time you observe weak lensing, you can observe both of them and see if they are equal or not. So we have observations about that. So far they are not very good, but with time we will get more precision, and the idea is really to get about that. And there is this project which is called Euclid. This is a European project, and they have a satellite which is going to start in 2020. And one of the main things is to observe that if these two potentials are equal or not. If they are not equal, then maybe we need two possibilities. One is to have some exotic matter which might produce a term here which is not diagonal. We can always add some exotic matter, that's a possibility. Or we modify gravity, because then we don't have this relation in modified gravity, because this is GR. If you modify gravity, you don't have the same equation. You have the same perturbation, the same metric, but not the equation, of course. So this is a consequence of GR in some sense. So that is one consequence, and I have 9 minutes. I'm going until 1.
Yeah.
Yes?
It's working.
Okay. Okay, now it works. Okay. So let us, if you have phi equal to psi, you're replacing these equations, and you get some differential equation for phi equal to the density of matter, for example, to the velocity, etc. And you get all the differential equations, and you can solve them with some initial conditions. Okay, so let me just focus.
It is only, you have only one scalar field, no?
Yes, now yes.
Only one.
Yeah.
Yes, because of this condition.
Yeah.
Yes, and that scalar field is related then to the density there, the density of matter, the perturbation of density.
Yeah, that's right, yeah.
So actually it's this. This equation is 8 pi g delta rho with a minus. And because we replace, so without this part, because this is just the background, just the perturbation here. You replace psi by phi, so you just have an equation for phi equal to this. So that is the equation that we have. We can have actually an additional equation, so let me go fast on that, because I might say some stuff on Friday about it, but not sure. But let me say it now.
You will show in Mathematica.
These calculations, yes, definitively.
So, you show second order also in Mathematica?
Yes, yes,
Second order.
yes. But second order, the level of action.
Okay.
not at the level of equations. I will explain why at the level of action actually. So the other equation is that, remember that we have g mu equal to 8 pi g t mu, and actually there is an identity which says that the covariant derivative of g mu is 0, so that says that the covariant derivative of t mu is 0. In some sense, matter is conserved. So now we have t mu, which is a t mu bar plus a delta t mu. So this equation, you can write it as also an equation at the first order. So you do these calculations, and then you get, of course, here the density of matter and things like that. And you define something, delta, which is the density over the background. So it means just the fluctuation of it. So then we can write an equation for delta actually, and you will have all the details in that. So I'm going directly to the last equation, and you can get a direct equation from this using all equations that we had. You start mixing them, etc., and at the end you can write an equation. Okay, so that is a very important equation also, and what it says is the following. This is the perturbation of matter normalized by the background value, okay? So it might be positive, it might be negative. If it is positive, it means that you have overdensity. It can be negative, you are in the voids, so you have a bit less density, etc. So this equation tells us about how this perturbation is growing in time, if it grows or not. What you see is that you have a second order differential equation. This term, which is first derivative, so it's like a velocity, it looks like a friction types of term. And the friction comes from the expansion of the universe. So what it says is that the matter is trying to grow, that the delta is trying to increase, but at the same time the universe is expanding. So it's opposing actually to the formation of structures. So this is the friction term actually. Because of the expansion of the universe, you get less clustering. So that is the interpretation of this. And here you have, of course, the density of matter itself, which is growing that. Now, if you look to a solution of that, you get two solutions. It's a linear equation. There is one solution, so some constant of integration a of t plus another a 3/2, I think. Is it 3/2? No, I don't have it here. Something like that. So you have two constants of integration, and so what you see is that when the universe is expanding, that will decrease. So that just decays, it goes away, it's not important, but this term is growing with that. So we say that even if there is an expansion of the universe, anyway, the structure will grow actually. So the delta matter is growing, and these are the structures that we are going to observe after. So that is very important because actually we can observe structures, so we can see how much they cluster, etc. And that is what this equation is saying. So now just to conclude about modified gravity, you take a theory of gravity, for example, f of r. You write the equation, and then from that, you do the perturbation exactly the same way. And you can write an equation exactly like this one, except that the gravitational constant will be some g effective, which depends on time. So I was saying before that there are some constraints on that this morning, that we know that g dot over g is extremely small, actually, less than 10 to minus some 17, something like that per years. Something like that. So we know that this has to be extremely actually almost constant. So that depends on the model of gravity you have, the parameters of your theory, the constant which appears, etc. So then it's a simple trick actually. You just, simple calculation. You take your equation of motion, you take the metric we saw in the Newtonian gauge, you do the calculations at the first order, and at the end you get an equation like that, and you can identify this. And that says if this is a modified gravity theory or not. If it is just G, then it's GR. If it is different than G, means that this is really a modification of gravity, that the gravitational constant is not the same. So it changes over time, it can depend also on space actually. So it can be a very complicated thing. In FOFR theories, it depends also on space. There's a paper by Shinji Tsujikawa about that. So then you can really constrain your theories, say that, okay, that should not change too much, so that will bring me some constraints on the parameters. So that is a game that you can play. And, but the theories that I will talk about, this screening mechanism, they're saying that at very large scales, this can be very different than G, but when you go at smaller scales, it becomes G. So in that sense, you recover GR. So that is the important thing, that at very large scales, you get something completely different, but at smaller scales, you get GR. So that is what we were talking about this morning, about these screening mechanisms that I will start talking about tomorrow. I will start by coming in, yes.
So this solution is valid for all scales, like on suburban as well as...
No, it is true in the linear regime of perturbations. So at very large scales. Now, if you want to go to smaller scales, you need to look to nonlinear theory, nonlinear perturbations. Yeah. Yeah. Sorry.
This is very for even for a linear theory.
Yes.
This is very fast subhorizon, superhorizon, or for both?
No. It's really at the Hubble scale. You don't go lower than that. But at very small scales, you forget about GR. You just do Newtonian theory, and in Newtonian theory, you take just a fluid, which is just the Euler equation and continuity equation of that fluid, and actually you will get the same equation somehow. So it seems to be that even at small scales, that works pretty well. As soon as things are not too large, as soon as these objects are not too large, even at small scales, it's okay. It depends where you are in the galaxy and things like that. That's the idea. Because I didn't talk about one equation to get that, is that you get the Poisson equation. You get a Poisson equation of this form. And the Poisson equation, the very fundamental thing, it is true even at very small scales, because if you walk in Fourier space, you have this. And at very small scales, k becomes large, but phi is very small. In a galaxy, phi is of the order 10 to minus 4 or 10 to minus 5. So gravitational potential, even at very small scales, remains small. So that is okay. The problem is delta m. Delta m can become very large, but the gravitational potential, even if you go, and this is the perturbation that we consider, even if you go at very small scales, at the scale of a galaxy, gravitational potential is small. This is why we used Newtonian theory until 19th century and no one noticed any problem, because finally these terms are really small, even at small scales actually. The only problem is that if you go at very small scales, yeah, the universe is not homogeneous and isotropic, so you cannot use that.